Hi everybody. In this physics video we are going to cover the topics of both lenses and mirrors. And in order to understand the difference between lenses and mirrors, we first need to talk about the differences between a converging light ray and a diverging light ray. So a converging light ray, as you can see, just describes how parallel light refracts towards a focal point. And so if we look at this diagram on the left, we see how all these parallel light rays are traveling towards this focal point after they're refracted. And so in contrast, when we consider a diverging light ray, it describes how a parallel light source will refract away from a focal point. And what's important to know here is that the focal point is the point at which all light is going to either diverge away from or converge towards. And so we have a sort of a definition here for the focal point. And what's also important about this focal point is that this is how the focal length is measured. And the focal length of a system corresponds to how strong that system can converge or diverge light from. So that's often how mirrors or lenses will be measured, is by their focal length. And so as you can see, the focal point is the point at which all light either converges or diverges to. So when we go back up to this image, we can see that here's the focal point, and then for a diverging lens or mirror, the light rays are going to refract away from that point. And for a converging lens or mirror, the light rays are going to refract towards that focal point. And this is important to know because when we start talking about lenses and mirrors, different lenses and different mirrors are either going to converge light or diverge light. So that's what we're going to get into next. So understanding the difference between a converging and diverging light ray is especially important as we consider both lenses and mirrors, because depending on what type of lens or mirror you have in question, that light is going to either converge or diverge. So as you can see from this very large diagram, for a convex lens, which is the first type of lens that we're going to consider, the light rays are going to converge. And so from this crudely drawn image, we can see that whenever light rays come into contact with this convex lens, the light rays are going to refract towards the focal point. So that means that it's converging. And the opposite is true for a concave lens. So when the light ray comes into contact with the concave lens, the light is going to be refracted away from the focal point. And so as we consider this focal point, we know that since we have to sort of imagine where this focal point is going to be, so we can draw sort of a dotted line. That means that this focal point is going to be negative. And so if the focal point is negative, that means that the distance from the focal point to the lens is going to be negative. So for a diverging lens, you should know that the f is going to be negative. And that's also true for anything that's diverging, as you'll see when we go over a mirror, that whenever you have something that diverges, the focal length is going to be negative. And so whenever you have something that converges, like for a convex lens, the f is going to be positive. And so as you can see for this thin lens equation, this is why this is important to know whether something's going to be positive or negative. Because when you apply, when you plug in a value for the focal length or the distance of the image or the distance of the object, it's important to know whether that will be positive or negative, as that will affect your answer for whatever you're solving for. So if you ever get a question that requires you to know whether it's a convex lens or a concave lens, you'll be able to identify whether that focal length or the distance of the image or the distance of the object will be positive or negative. And so one note, as you'll see later, the distance of the object is always going to be positive 100% of the time. But what's not true is that the distance of the image, essentially the distance of the image can either be positive or negative. And so as you can see from the second part of the diagram, depending on whether the distance of the image is or positive or negative, shows whether the image will be real or virtual. And so a real image or a virtual image is defined as by what side of the lens the object is. And so depending on whether you have a real or virtual image, the image is going to be upright or inverted. So for a real image, what is always true is that a real image will produce an inverted image, essentially. And for a virtual image, it will always produce an upright image. So if you follow this arrow around, we know that for the real image, it's going to produce an inverted image. And so what we're going to talk about next is magnification, how this relates to magnification. So if we have the equation here below, which I'm sure most of you have seen, we can plug in the values for distance of the image and distance of the object to solve for the magnification. And so one thing that we can know is that if we're given a concave lens or a convex or a convex lens, we can determine whether that image will be real or virtual. And so if that image is real or virtual, we can identify whether the magnification should be positive or negative. And that'll help us eliminate a few answer choices as we're going through questions. So I kind of want to work through this one last time. And so we're going to start with a convex lens. So a convex lens, I know, is always going to converge the light rays. And if the light rays are converging, that means the focal point and the focal length is going to be positive. And so if the focal point is positive, or the focal length is positive, then that means that it's a real image. And so this, I can draw a line, is going to correspond to a real image. And so that means if the image is real, then that means the DI, the distance of the image, has to be positive. So if the distance of the image is positive, then the image is going to be inverted. And as we continue, if the image is inverted, the M will be negative, because if we plug in a positive value for DI, we're going to end up getting a negative value overall for the M. And so if we consider the opposite, such as a concave lens, then we know that this concave lens is going to be diverging the light rays. And since the light rays are diverging, F is going to be negative, and if F is negative, then we know it's a virtual image. And what we know to be true for a virtual image, the distance of the image is going to be negative, and if the distance of the image is negative, follow this around, the image is going to be upright and the M is going to be positive, because as we plug in a negative value for DI into this equation, we essentially get a negative DI over DO, and this will be plus, so that'll be a positive magnification. So if you'd like to screenshot, you can turn the video back and go ahead and screenshot this diagram for a convex lens and concave lens, because next what we're going to talk about is mirrors. And mirrors can get a little bit confusing when you compare them to lenses, because a lot of the information is just exactly opposite. And so the first thing we're going to show you is that once again we have both a concave mirror and a convex mirror. So just like how we had a concave lens and a convex lens, we also have a concave mirror and a convex mirror. And so as you can see from the image that's drawn, here is your mirror, and then here in the gray are the light rays that are coming into contact with the mirror. And so depending on whether that mirror is concave or convex, it's going to either converge the light rays or diverge the light rays, as you can see. So first let's go over the concave mirror. So the concave mirror, when these light rays come into contact with it, are going to converge, meaning they're refracting towards the focal point. So that means that the focal point has to be positive since it's converging. And so the opposite is true for a convex mirror. As the light rays come into contact with the convex mirror, they're going to refract away from the focal point. So that means the focal point is imaginary. And if the focal point is imaginary, then that means F is negative. And so depending on whether you have a positive or negative focal point or focal length, then that means that the image is going to be either real or virtual. So for a positive focal point, the F is going to be the focal length. The image is going to be real. And if we have a negative focal point, that means the image is going to be virtual. And so depending on whether we have a virtual or a real image, as we went through for the lenses, will tell us whether the distance of the image is positive or negative. So for a positive focal point, we know that the image is going to be real. So if the image is real, that means our distance of the image is positive. And I want to kind of show you that this is opposite of what we have for lenses. This is the same as what we have for lenses. So as the distance of the image is positive, that corresponds to a real image. And same for the lenses. Distance of the image is positive, we have a real image. And so let's go through the convex mirror now. So as the F is negative, that's going to produce a virtual image, and if it's a virtual image, then the distance of the image is negative. And we can once again go ahead and follow this through. follow the arrows through. So if it's a virtual image, then the image is going to be upright. And if it's a real image, then the image is going to be inverted. And this is always true, that a virtual image will produce an upright image, and a real image will produce an inverted image. And so depending on whether the image is upright or inverted, the M will be positive or negative. And so you can go ahead and screenshot this, or rewind the video and screenshot it when there's no markings on it. But this is essentially all that you need to know for a concave mirror or a convex mirror. And so here's just some additional helpful hints and just a summary of what we've covered. And so like I said earlier, whenever you have a converging light ray, the F is going to be positive. And so whenever you have a diverging light ray, the F is going to be negative. And so this is really important because this helps us understand whether the image is going to be real or virtual. So like I stated, whenever we have a positive focal point or focal length, you're going to get a real image. Whenever you have a diverging light ray, the focal length is negative, and that means the image will be virtual. And so as you can see, depending on whether that image is real or virtual will tell us whether the image is upright or inverted. So just restating everything that I've already said, real images are inverted and virtual images are upright. And so one last additional thing that I'd like to add into this video is that if you ever encounter the radius of the curvature for a spherical mirror, spherical lens, the radius of the curvature is exactly 2 times the focal length. So in this video, this basically covered all of the very basics for concave and convex lenses and mirrors, and basically how these lenses and mirrors will either converge or diverge light.